At Bookworms, hi! Thanks for joining me again in this lesson. As I promised in the previous lesson, that this one is going to be awesome. Now recall that in the previous lesson, we closed off calculations on work. Like I closed off by showing you how to calculate the work done by the force of gravity on an object that's moving down an inclined surface. Now, I also closed off by mentioning the work-energy theorem, saying that is how we actually bridge the section on work and energy. That's how we integrate the two. And recall our definition of the work-energy theorem. We said that the work-energy theorem states that the total work done on an object by a constant force is equal to the change in kinetic energy of that object. And I also mentioned that you would be able to calculate the mass or the speed or the displacement of the object if you just work around the theorem and that formula. Now, in today's lesson, this is precisely what we will be doing. Now, with me, I have a physical sciences question paper. Yes, you guessed right, paper 1, and it's from the Northwest Province. We'll be specifically looking at question 5, which is on work and energy. Now, drum roll, as you get down to business. Now, our case study. The diagram below shows a crate of mass 50 kilograms sliding down a steep slope. The slope makes an angle of 30 degrees to the horizontal. The motion of the crate as it moves down the slope is controlled by a worker using a rope attached to the crate. The rope is held parallel to the slope, and the tension in the rope is 300 newtons. And a constant frictional force of 50 newtons act on the crate as it slides down the slope. Now, take a moment to digest that case study. Now, the particular question we will be looking at is the subsection, question 5.4. And it states, the change in kinetic energy of the crate is 450 joules as it slides from the top to the bottom of the slope. Use the work-energy theorem to calculate the length of the slope, that is delta x. Now, we went through the case study. We went through what the question requires. Now, if we look at the data that is given to us, we have our mass, we have our angle of inclination. We are told that a worker is keeping the box constant, is controlling the motion of the box by means of a rope, and we are told that the tension in the rope is 300 newtons. We are also told that the slope is exerting, or rather the surface is exerting, a frictional force of 50 newtons on the crate. Now, what are they looking for? They're just looking for the distance covered by the block. Now, as we go back, let's just quickly look at what we have. We are given the change in kinetic energy. Bingo. Okay? Now, the work energy theorem says that the total work done is equal to the change in kinetic energy. Now, can you see where this is going? I mean, we already know that the total work is equal to the change in kinetic energy. We are given the change in kinetic energy, which is the same as our total work. So there we have it. We already know that our work net is equal to the value that's given, which is 450 joules. Now, if you trace back your steps, you already know that the work is equal to your force times your displacement. But let us revisit the definition of the work energy theorem. It says the total work done on the object is equal to the change in kinetic energy of that object. Now, if we look at the total work. What comprises the total work? The total work, if you recall, it's basically the work done by all the forces acting on that object. Now, what are the forces that are acting on that object? Well, we already know that we have the tension by means of the rope. I mean, the worker is controlling the crane. So we have the tension of the rope there. That's our tension force. It's there. We also have the force of friction. It's there. They gave it to us. They told us about the force of friction. What else is there? What else is there? I mean, you do recall that in our previous lesson, we spoke of the component of gravity that is parallel to the surface. And yes, that is it's there. Hence, the worker is controlling the motion of the crate by means of a rope. So there we have it. You have your tension force, you have your force of friction, and then you also have your F parallel, which is your component of gravity parallel to the inclined surface. Now, the total work is equal to your force of friction, your tension, as well as your F parallel. Okay, we're good. But if you take a look at this, we have our work net, and it's equal to, let's start with the force of friction, that is our F, yes, delta X cos of 180, precise, because friction works in the opposite motion to an object. And then plus the tension force, yes, you have your Ft delta X cos, precise. As you saw in the question, in the diagram on the screen, tension is working opposite to the motion of the object as well, opposite the crate. So that's cos of 180 degrees as well. And then we have your F parallel, which is, okay, that's your F parallel, delta X cos of 0. But you also know that your F parallel is equal to mass times gravity sine your angle of inclination, which is 30 degrees. And then follows your delta X cos of 0. Take time to absorb what's on the screen. Now, I've laid it all out. You know that if it's cos 180 degrees, it means it does negative work. Take a look at the diagram. Friction does negative work and tension does negative work. However, F parallel does the negative work because the crate is moving in the same direction as F parallel. And recall that in the previous lesson, we said that the 30 degrees is our angle of inclination, and that's the angle we substitute in our F parallel formula. Right now, what's left is just to take out the common factor, which is our delta X. After all, the main aim of this question is to find delta X. Now, delta X into your force of friction, which is 50 newtons, cos 180, that makes it minus 50. And then that's positive. Your tension force, which is 300 newtons. That's 300 newtons cos 180, which makes it minus 300 newtons. What else do we have? Well, we have F parallel, which is mg sine theta. Our mass, the mass of the crate is 50, and then multiplied by 9.8, that gives us 9.8 sine 30 degrees, which is 0.5, which then cos of 0 makes it positive. Yes, it's 50, mass of the crate is 50, multiplied by the gravitational acceleration, which is 9.8, multiplied by sine of 30, which is 0.5, times cos of 0. Now, as you can see in your calculations, this narrows down your F parallel to 245 newtons. Now, if you go back to all that you've substituted and sum up all your forces, that's minus 50 minus 300, and minus 245. Now it all sums up to minus 105. Now that's the sum of all your forces that are acting on that object. The sum of all your forces acting on that object, it all adds down to minus 105 newtons. Now if we go back to our definition of work, it's just your force times the displacement. So now what do we have? We have minus 105 times delta x. Now remember that delta x is what we are looking for. We are looking for the distance traveled by the crate. Now we know that our total work is 450 joules. Basically what we have to do now is rearrange the equation and make delta x the subject of the formula. Moving down, we then have delta x is equal to 450 newtons minus 105, and that will equal to 4.29 meters corrected to 2 decimal places. Now 4.29 meters is the distance traveled by the crate down the slope. Now you can already tell that this has been a very simple problem to solve using the work-energy theorem. Now in the next lesson we will be proceeding on moving from the work-energy theorem to talk more on the conservation of mechanical energy. We will be talking energy principles. Now, I trust that this has been very informative. I trust that you have enjoyed yourself. I know I have, and I look forward to seeing you in the next lesson. Remember, at Bookworms, learning is fun to mental. Cheers.